So thanks everyone for coming. This is the last of our the UMI group on Socio-Epidemiological Modeling seminar series. And today I'm happy to present our speaker, Francesco Regazzoni, who's a assistant professor at Politecnico di Milano. I've known Francesco for, gosh, I guess it's been like 10 years or so now. We had courses together when we were both PhD students, and so he's done a lot of work in some work directly kind of in socio-epidemiological modeling, as well as a lot of work I think that's very much adjacent and relevant to it, particularly in equation discovery and kind of latent dynamics work on time series and dynamic modeling. So with that, I'll go ahead and give the floor over to Francesco. So thank you very much, and we look forward to hearing your talk.
Thank you very much, Alex, for the introduction and also for the invitation. So I'd like first of all to introduce the general framework of this presentation. So we'll talk about time-dependent problems. So we will consider models in the form that you can see here. So we have a state variable that we can call big X that evolves according to a differential equations where U is an input. And then we are typically interested in some output variables that we denote by Y, and so G will be the observation operator mapping the state variable with the output. So you can see this high fidelity model or full order model as a map from input to an output, where an output can be either a scalar output or even a space-dependent output, so what we'll call a field. And the main goal of this will be to find what we'll call a reduced order model or a surrogate model, that is another model with a different state variable small x, but such that the map from the input to the output variable is as close as possible to the one of the high fidelity model. So this has been often called the model order reduction, and nowadays we often call it also surrogate modeling. And you can do it either by projecting the high fidelity model on a lower dimensional subspace, or you can do it in a data-driven way. So with a high fidelity model, we generate some input-output pairs, so pairs of U and Y, and then we try to infer this surrogate model, to infer the dynamics that allows you to link U and Y. So why should you do that? Well, for several reasons. One, if you have many query scenarios like UQ or inverse problems, you need to evaluate several times repeatedly this input-output map, so you want to do it in a cheap way. Or if you want to reduce the dimensionality of your model, or maybe you don't even know the high fidelity model, you just have data, and so we want to learn a model, so to discover a model directly from the data. So in other terms, what we want to do is to observe nature, so to take measurements and to try to infer the laws that can explain these measurements. So this has been done for years, prerogative of humans, but now we would like to see whether we can construct algorithms that are able to automate this process. And I will split this talk in two parts. First, I will consider the case where the output is a scalar, and then we'll consider the case where the output is a space-dependent output, so it's a field. So here the framework that we will consider is that we have some input, we have some output, and we would like to fill this black box that allows us to link the input to the output. And the method that we developed is called model learning, as we are learning a model. What are the data? Data are input-output pairs, so are continuous functions. So input and outputs are both continuous functions of time. Then we need to select a hypothesis space, that is the class of candidate models where we look for our reduced order model or surrogate model. And we decide to focus on systems that can be described as systems of ODEs, ordinary differential equations, where we need to select the right-hand side half and the observation function G. And so we need to select two suitable subspaces of Lipschitz function and of continuous functions. And once you've done it, you can write your model learning problem as a best approximation problem. That is, we will look for the model belonging to this class of candidate models that minimizes the mismatch between the observations, your data, and the predictions obtained by the model. So what we need to do is to select a space of candidate right inside F and the observation function G. And it turns out that you can choose these spaces in a smart way, in the sense that if you choose a subset of discrete and continuous functions that are dense on compact sets, then it turns out that your hypothesis space is dense in the space of all the possible dynamical systems. Or in other terms, for any prescribed accuracy, you can find a model belonging to the space of candidate models that approximate within that accuracy any possible model. And it turns out that neural network satisfies these assumptions. And so this led us to the idea of representing both F and G with two neural networks. So this is the neural network that we got. It is composed of two subnetworks. The first one evolves the dynamics of your state that we will call a latent state, as it doesn't have an immediate physical meaning. It is conditioned on the physical input, so input signals and input parameters. And as an output, we have the time derivative of the latent state, and you can use it to update with your favorite time-stepping scheme, your latent state. And then you have a second neural network that works as a decoder, in the sense that it takes as input the latent state at a given time and outputs the physical output at that corresponding time. So this recurrent part is formally similar to a neural ODE, although we don't know a priori the dynamics of X, but we are discovering actually a latent space. And this latent space discovery will be done by training simultaneously the two neural networks, with the dual purpose of both be able to represent the output and also to represent the dynamics. And as I will show later, this has several advantages with respect to methods that instead first construct an encoder and then an autoencoder and then learn the dynamics. So we tested this kind of method on several benchmark test cases, including system of nonlinear ODEs, parabolic PDEs, and hyperbolic PDEs. So for instance, here we would like to predict the movement of the center on the midpoint of the string, of an elastic string, as a function of the movement of the ends of the string. And in all the cases, we observe that as we increase the number of latent states, so we enlarge the capacity of the hypothesis space, we can increase the accuracy, and we have an exponential increase of the accuracy. So this is observed in all the cases. In the parabolic case, and also hyperbolic one, we can see that we can outperform methods based on linear projection. Now I'd like to show you a few applications in the field of cardiac modeling. That is my favorite field of applications, and what I'm going to present is done in collaboration with Alfio Quarteroni, Luca Dedè, and some work also with Matteo Salvador. So first of all, let me introduce what is the cardiac model that we are using for those of you who are not familiar with cardiac modeling. So first of all, we describe cardiac electrophysiology, so the activation from the electrical viewpoint of the heart, and this is done by means of nonlinear parabolic reaction PDEs that describe how the electrical signal travels through the heart. Then we have a second model that acts at the microscopic scale that describes how the heart generates force. So here the input is a ionic concentration coming from the electrophysiology model, and the output is the amount of active force, which in turn is the input of the tissue mechanics model that accounts in this way of also the presence of an active stress. So here we have the equations of elastodynamics. And finally, the tissue mechanics model is coupled with the blood circulation model, and very often we use the lamp parameters model for blood circulation, so zero-dimensional model that exploit an analogy with an electric circuit, so between an electric circuit and a circulatory system. Then we also have some feedback, so all these models are coupled together by a very complex network of interactions, which make the numerical approximation of this kind of models very challenging. So, given this model, given its complexity, we have first to focus on these part of the model, it is the active fourth generation model, that very often is the bottleneck, because despite being a microscale model, it is a very complex one. So in particular, we were dealing with high fidelity model with nearly 2000 variables. So our approach to reduce the computational complexity of the whole model was that of using this subcellular model to generate a simulation database, so a large number of simulations, and then use model learning as a way to construct a surrogate model for this high fidelity model. And after having validated it against the high fidelity model, we were able to deploy the pre-trained neural network at each degree of freedom of a computational mesh of the three-dimensional finite element model. So in this way, we had a finite element model that were fueled at the micro scale with a reduced model based on a neural network. And the results are summarized here. So we had an accuracy of nearly 3 orders, so 10 to the minus 3, with a very good speed up with 3 orders of magnitude of memory saving. So this was a first example. Now a second example of application, where instead we will focus on the reduction of the whole three-dimensional model. So I will use these two symbols to denote the three-dimensional model, so the electromechanical model, and this symbol to denote the blood circulation model, so the zero-dimensional model that accounts for the blood circulation. So you need to take into account that both two models depend on some parameters. So what we do when we need to apply this model in a clinical setting is that we fix the numerical value of the parameters. We provide them as an input to the two models. We couple the two models together, and by running a simulation, we are able to collect transient of pressures and volumes. And finally, we extract some quantities of interest, such as the pressures, minimum and maximum pressures, the volumes, minimum and maximum volumes, and so on. So this defines a map from the parameters to the quantities of interest, which is a static map. And so this led several research groups in the world to the idea of constructing an emulator that is a machine learning model that replaces the whole map from the parameters to the quantities of interest, which is of course a very clever idea. This allows to have an impressive speed up, although it has some pitfalls, because here we are totally missing the time dependence of the model. So we are totally missing the fact that we have a time evolution, and so we will not be able to extrapolate over time. So we took a step back and we came up with the idea of surrogating only the three-dimensional model. It is the one that is computationally expensive. So we leave the zero-dimensional model in its high fidelity form. In the end of the day, it doesn't need a reduction. In this way, we will be able to actually run simulation and also hopefully to extrapolate over time. What is the limitation here? What is the drawback? The drawback is that now we don't need to learn a static map, but a dynamical model, which is more challenging. But we have the technology, we have model learning, and so we applied our ideas to this problem. And these are the results in a nutshell. So here are quantities of interest that are predicted against the ones obtained with the finite element model. So they are parity plot between neural network and finite element simulations. You can see that the match is very good. Also, accuracy is very good, and especially if you consider that we are able to extrapolate over time. So we use a test time horizon that is twice as long as the training one, but the accuracy is not deteriorating. The computational speed up is very good. We go from 4 hours for a single heartbeat on a cluster with 32 cores to 1 second on a normal laptop. So we go to real time. Of course, to gain that, we have to pay a price that is training cost. So we have 18 hours of training cost and nearly 120 hours to generate training data. So the question here is, does this pay off? Does this pay off? So it is worth to spend this amount of time to save 4 hours? Of course not if you need to run a single simulation, but it is convenient whenever you need to run many simulations. For instance, if you want to do a Bayesian parameter estimation, so this is an example of use of this kind of model in the context of estimation of the parameters under uncertainty. So here we would like to estimate some parameters of the model given the output. And this can be done, for instance, by MCMC algorithms. that are basically random walks in the space of parameters, where at each step you need to run a simulation to estimate the likelihood that tells you whether to accept or reject the step. And we estimated that to reach statistical convergence, we needed almost 1 million of heartbeats of simulation. And if you had your own cluster computer with 160 cores, this would require 87 years of continuous simulation. So something that cannot be done, of course. Instead, by using a surrogate model, you can sample just 30 values of on the parameter space. You run your high fidelity model for those 30 samples, and then you train a surrogate model and you run the MCMC algorithm by using a surrogate model. So in this way, we spend nearly 120 hours to generate the samples, 18 hours for the training, and just 13 hours to run the MCMC algorithms. So in the end of the day, we can obtain results in less than 1 week of simulations instead of 87 years. And remarkably, within the Bayesian framework, we can also account for the model error that is introduced by replacing the high fidelity model with the surrogate model. Okay, so after these two examples, I'd like to introduce a new ingredient that I haven't introduced before, that is intersample variability. That is the fact that all the samples can be different one from the other, and they can be different maybe because of some features that are not even measurable. And so this is an extension of this method that I developed with Dominique Chapelle and Philippe Moirot. So the starting point is the method that I presented you before, that, however, doesn't account for intersample variability. So given an input, the output will be always the same. The point is that each sample can depend on some parameter that cannot be measured. So what we'll do is that we will introduce within the inputs of the neural network a sample-specific latent parameter. So a parameter that depends on the given sample and that is latent in the sense that we will not measure it, but we just know that it exists. So how can we deal with this object if we cannot measure it? Well, the idea is that we will learn it. So during training, we will not optimize only for the weights and biases of the neural networks, but we will optimize also for this latent parameter associated to each sample. But what can we do whenever you have a new sample, since you cannot measure the latent parameter and it doesn't have a clear physical meaning? Well, you can infer it by observing your output for a short time windows. So we have an observation time windows. We solve an inference problem where we optimize with respect to the latent parameter in order to minimize the mismatch between the model output and the observations. And once this inference is over, you can use the observed latent parameter to predict the future evolution of your system. And so we apply these ideas to a couple of cases. So this is a proof of concept in the sense that data are generated synthetically in the setting of hypertension. So hypertension is a multi-scaling time process because it involves a fast scale that is heartbeat with a slow scale that is the long-term remodeling of the of what at the fast scale is seen as a parameter, okay? So what we did was to generate data through a synthetic model. Then by using this data, we generated also heartbeats by using the cardiac model, and then we added noise. And then starting from a noise data, we try to reverse the process. So first, we use data simulation techniques at the fast scale to try to infer the slow scale evolution of these parameters. And then we use model learning with latent parameters to try to learn a model that can explain this long-term evolution. And then we use it to try to predict the evolution of unseen patients. And we were able to get a relative error of 2%, so something that is acceptable in applications. And here, the latent parameter that is used that is associated to each patient can be associated with the disease severity, and so it can be even used for patient stratification. A second application instead is in the field of epidemiology. So this is a work done more recently with Giovanni Ziarelli, who did most of the work, Stefano Pagani, Nicola Paolini, and Marco Grani. So I think that there is no need to introduce this audience the importance of forecasting epidemic events. And you know better than me that we have several mathematical models, like the SERI model that you can see here, that can be used to forecast epidemic evolution. The point is that in this model, we have this parameter beta, that is the transmission rate that can depend on several exogenous variables, such as environmental variables, temperature, humidity, vaccination profiles, non-pharmaceutical interventions, and even strain-specific virus features that cannot even be measured. So our goal is that to learn a model for the evolution of the transmission rate parameter, beta, that depends on these kind of exogenous variables that can be measured or not even measured. So we developed an architecture that is somehow hybrid, in the sense that we have a data-driven layer and a physics-based layer. The physics-based layer is based on the same model, and the data-driven layer will allow to learn the evolution of the beta parameter. So this will allow basically to learn the features that are not modeled by the same model. And here we use a similar architecture to the one I presented before. So we have this neural network that is a recurrent one, basically a neural ID that evolves the beta parameter, and it is conditioned on two kinds of inputs. First, measurable variables, such as temperature and humidity. And second, by a sample-specific latent parameter, like the one that I mentioned before, that will account for the specific features of every wave of the epidemic or every strain of the virus that cannot be directly measured. And importantly, we will train the models and the latent parameter in an end-to-end fashion together with the same model. So we will, in our loss function, we will account for the fact that the beta evolution will have through the same model on the curve of infected people. So our loss function will account for the infected people, and we will differentiate through the same model. So this is about training. What about inference? We'll proceed as I mentioned before. So we will observe the curve of infected for a short observation window. We will initialize randomly both initial parameter, the initial value of beta, and the sample-specific latent parameter. And then we will do inference on these two variables in order to minimize the mismatch between the observation and the predictions within the observation windows. And then after inference is done, we can use the model to do prediction. So we can predict what happens after this observation window. And we applied these ideas to real data from influenza in Italy between 2010 and 2020. Here, input data are temperature and humidity that we took for a public archive of ilmeteo.it, which contains data of temperature and humidity in several cities. Then we do a large work of data aggregation and cleaning to reconstruct curves of temperature and humidity across these 10 seasons. And instead, for output data, we took influenza waves in these 10 seasons coming from an Italian epidemiological and virological influenza surveillance system. And here are the results obtained with the leave one out approach. That is to say, we train with the 9 seasons and we try to predict the 10th seasons in a cyclic way. And so this is a sort of average results that we can obtain. So with 7 weeks of observations, so we observe these green windows of time, and then we can predict the evolution of the epidemic event. And here you can see also an estimation of the certainty thanks to multiple training. And in one case, we got better results. That was the year 2018-2019, because here we predicted a peak that was too early, even though we were able to predict the magnitude of the peak. But you can see that if you are more patient and we consider an observation windows that is twice as long, we can predict also the moment of the peak. So you can say that the quality of the predictions is refined as time goes by and you acquire more and more information. And a nice feature of this approach is that it also allows for some interpretability of the model, as it is not a purely black box model, but it is a hybrid model mixing a data-driven approach and a physics-based approach. So to do that, we plotted in the phase space the impact of the 3 input variables, so temperature, humidity, and the latent parameter. And you can see that we have the presence of a an unstable and a stable equilibrium. For instance, the effect of temperature is to move it right toward the unstable equilibrium. And similar consideration can be done for humidity. And for the latent parameter, in this way, we can also give a physical interpretation to the latent parameter. So let's say some insight as a measure of the severity of that specific wave of the epidemic event. Okay, so now I'll switch to the last part of the talk, that is a space-time operator learning, and this is done in collaboration with Alfio Quarteroni, Luca Dedè, Stefano Pagani, and Matteo Salvador. And going back to the previous slide, now we switch to the case of scalar output to the case of space-dependent output. And of course, what you can do is that you take your space-dependent output, you discretize it by means of your favorite discretization method, for instance, finite elements, Fourier series, or whatever. And after discretization, you can go back to the previous part of the talk and apply those kind of approaches. However, you can do something better that accounts for the space-dependent nature of the variable that we are considering. And to do that, we developed this sort of extension of the previous method that we call the latent dynamic networks, in which, again, we have two subnetworks. The first network evolves the dynamics of a latent state that here we call S, but yeah, it's just the change of name, but it's what we called X before. So it evolves the dynamics of this state, given as an input the physical input, so this time-dependent input after normalization. And then we have a second neural network that acts as a decoder, because it takes the latent state, it allows to reconstruct the solution at that time. And importantly, this time, the decoder will take as an input also the physical coordinate of the point where you want to construct the output. So in other terms, if you want to reconstruct the output, you will need to query several times this decoder, each time for each value of x where you want to know the solution. And this way you will reconstruct the output. So this is what is very often called a neural field that is conditioned, in this case, on the latent state. So how can you interpret this latent state? Well, this will be a low-dimensional encoding of the state of the high-fidelity model. However, this latent state, so this latent state, this encoding is not constructed a priori, for instance, through an autoencoder, but it is discovered automatically during the training. And as I'll show you, this has several advantages. One of them is that since we don't need to construct an autoencoder, and thanks to this coordinate-based representation of the output, we never need to work in high-dimensional spaces. So all the variables that you are here are small dimensional, and this way this allows for a very lightweight architecture that is easy to train, and it has very good generalization capabilities. So here I'm going to show you some test cases. This is a benchmark case, a diffusion reaction problem, linear problem where we have a forcing term that is a sine wave. We give it a frequency and a given with a given frequency, where instead we vary the amplitude and the phase. And this test case is designed in such a way that the output will be a sine wave as well. And being a sine wave with a given frequency, this can be fully described by means of just two variables that are amplitude and phase. So here we have a solution manifold that has dimension that is exactly equal to 2. And so this makes this test case an ideal test bed to check whether or not latent dynamic networks are able to discover this two-dimensional representation. So we're trying to train latent dynamic networks with a training set of 100 simulations with 100 points in space and 100 instants in times. And then we tested it on 1000 samples. So you can see here a subset of the testing sets. So each box is a simulation. On the left, you can see the full order model solution. On the right, the reduced order model solution. And here the trend of the error as a function of the number of training samples. You can see that with as few as 25 samples, you can have an accuracy that is smaller than 5%. And as you increase the number of training samples, we can extract more and more knowledge. And since, as I mentioned, here we have a dimension of the space that is just 2, here it is nice to try to interpret what is the latent space that the model discovered. And to do that, we try to plot the real and imaginary part of the Fourier transform of the solution in the space of the two latent variables. And you can see that there is a quite clear relationship between the latent variables and the real and imaginary part of the Fourier transform. So we can see that the LDNet model discovered a sort of compact encoding that is somehow equivalent to the Fourier transform, even though we didn't instruct it to discover the Fourier transform. As a second test case, instead, it is unsteady Navier-Stokes equation. So here we have a lead-driven cavity problem where we make the velocity that we apply on top time-dependent. And so by making it time-dependent, we have the creation of vortex structures, the destruction of vortex structures, so a very complex scenario. So here we train on 100 samples of length 20 seconds, let's say, and then we tested on 2000 samples of length 40. And you can see that we are very accurate even in time extrapolation, so the accuracy is almost the same in time extrapolation and in time interpolation. And again, as you increase the number of latent states, so you make the capacity of the model larger, we can make the surrogate model more and more accurate. And at the end of the day, we can get accuracies that are of the order of 10 and minus 3. And finally, third test case is instead from the domain of cardiac electrophysiology. So this is a one-dimensional substrate that can be excited. So we stimulate the substrate in 2 points randomly in time. And you can see on the bottom what happens. So now the simulation is running. So when you stimulate it, you have the creation of a wave that propagates. After some time, we stimulate maybe also another point, so the two waves can collide. So you can see that this test case is quite challenging. It has several features that make it quite challenging. And so we try to test to compare the performance that we can obtain with our method. It is the last column with state-of-the-art methods. So we compared it with the POD methods combined with DAME, so methods based on linear projection. That is totally ineffective in this case because of the wavefront traveling nature of this problem. Then we also compared our method with methods based on autoencoder, where we first try to find a compact encoding and then we try to learn the dynamics by means of LSTMs or neural OEEs, also with the final training in an end-to-end fashion. And you can see that our method is the one that achieves a higher accuracy. Here you can see from a quantitative viewpoint, we have an accuracy that is almost 4 times larger. And most importantly, you can see here the distribution of the error in the training and in the testing data set. You can see that while the other methods suffer from overfitting, as the error in the testing dataset is larger than on the training dataset, our method is the one that has lower overfitting. And you can understand it if you look at the number of training parameters. So whereas other method requires order of 20,000 parameters, our method requires just 2,000 parameters. So it is more parsimonious, and thanks to this being parsimonious, is able to generalize better. Finally, this is the same case, but in 2 dimensions, which is more interesting because we can have bifurcations, in the sense that depending on the timing and the position of the stimulation point, you can have 3 behaviors, either a reentrant driver that is self-sustained, or a focal activation, so a single activation, or the tissue can be refractory, and so nothing happens. And you can see that our method is the only one that is able to capture this bifurcation, whereas other methods suffer from artifacts. And indeed, the accuracy is 5 times larger, and we use only 2,800 parameters instead of more than 1 million. that are required by the other method. And with this, I thank you very much for your attention. And if you are interested, you know anyone that can be interested or working on these topics, just drop me an email because I'll have soon a postdoc position that will be open. Thank you very much. And if you have questions, I'll be happy to take them.